All right, so again, a zero, any root, zero or a root is the real number value when the output is zero. So simply we're talking about the x-intercepts. So what on the example would be -1 and 4. You can read it right off the graph on that one, pretty simplistic. If we wanted to do it mathematically, then we're going to put in 0 for the y. Doesn't matter whether it's linear, quadratic, a circle, ellipse, hyperbola, a root, could be a square root, could be exponential growth, could be exponential decay, it could be all of those, absolute value. How do you find the zeros? Mathematically, put in 0 for the y and solve for the x. Jeff, here's your quiz and homework. Okay, so right here all we're doing is substitute 0 in for the y and solve for x. It should make sense. You need an x value for a 0. So you need to leave x in the equation. So you put 0 in for y, solve for the x. And quite frankly, if you ever want to get a y-intercept, put in 0 for the x and solve for y. Pretty simplistic to solve mathematically. Let me get rid of my screen so I can go higher. All right, so find the zeros. So you guys just saw me do one a minute ago on the quiz. So go ahead and find the zeros for that function right there, that quadratic function. And I'm going to pause the video. All right, so again, if you're not the greatest at factoring, you got to fix that because your math from here on out involves a lot of factoring. So hopefully you factor that. 2x minus 5x plus 1, set each equal to 0 and solve. So really what happens is when you put 0 in for the y, you should say to yourself, I have a quadratic equation. How do I want to solve this quadratic equation? I can factor it, set it equal to 0. I could take the square root of both sides if there's no x to the first power, or I could use the quadratic equation. And that would be the answer. And quite honestly, sometimes you'll get the zeros by simply taking the square root of both sides. However, sometimes if it's quadratic, you'll have to find the zeros by using the quadratic equation. Okay? All of those are possible. All of that is possible. All right, let's do the second example. So we need to find the zeros here of this one, and let's see. I'm going to make life easier. I am actually going to multiply both sides. So let's put in 0, right? Let's multiply everything on the left by 3, and let's multiply everything on the right by 3. Everything on the left by 3, everything on the right by 3. I'm getting rid of the 1/3. You can try to factor it if you want, but I'm just going to get rid of the 1/3. Left is 0. The right becomes 3 times 1/3 is 1, x squared. 3 times x is 3x. And 3 times -18 is what? -36, 46, 54. So you got 0 equals x squared plus 3x minus 54. Let's see if we can factor this. And if it doesn't factor, what are you going to do? Quadratic equation. And sometimes you're going to have to find the zeros. Okay, so if it factors, great. If it doesn't, quadratic equation. So again, remember factoring. Hey, I got a 3 in mind for the middle, right? Positive 3. What multiplies to a 54?
6 and 9.
6 and 9. Oh, and are they 3 apart? Oh, well, la-di-da, right? Fancy that. 6 and 9. And the middle's got to be positive, so the 9 better be positive and the 6 better be negative. And we end up with x equals 6, x equals -9. Now you could have played around with the 1/3, but that would be a pain. But you could get there. But it was a little bit easier to get rid of it. Just got rid of the fraction by multiplying both sides by 3. So 6 and -9. You say, Mr. Scarvey, I would have never known to do that. Yeah, I know. That's why I did this one. All right, to show it to you, get it in your thinking, and get it as a possibility. What's the reality? You got to find a 0 mathematically, put in 0 for the y, solve for x. It's quadratic, 3 possible ways to solve, and away you go. All right, number 2, to find the values of the y-intercept algebraically, again, substitute 0 in for the x, and solve it for the y. Let me just pause 1 second here on 2. So you look at what we have here, and you're going to say, okay, this is quadratic because it's squared. Oops. And it's a function because there's 2 different variables, right? So we got a quadratic function. If you had something like this, don't write this, but y equals negative 2x over 5 minus 7, you would say, oh, that's linear. And it's actually in slope-intercept form, and if they asked you the y-intercept, you would say negative 7, right? If they gave you something linear, like, again, don't write this, 2x plus 5y equals 20, you have 2 choices. You can put it in a slope-intercept form, y equals mx plus b, and read the b, right? Or you could still do it mathematically, put in 0 for x, so that's all 0. Solve for y, looks like y equals 4 to me. So the y-intercept on that is the 0.04. Okay. We're doing quadratics, so again, in this scenario, we're going to put in 0 for the x. So let me get rid of all this junk. So all we're doing is putting a 0 in for each x. Might as well write it out the first time here. But you can see all the variables where the x is, they just go away. So in this case, y equals negative 5. And if they asked you the coordinates of the y-intercept, then it would be 0, negative 5, right? Pretty simplistic. Say, Mr. Scarfy, why did we get 2 zeros and we only got 1 y-intercept? Because when you put in 0 for the x, the squared term is gone. However, in the previous one, when you put 0 in for y, you still have a squared variable. And you should be expecting 2 solutions, right, with a squared variable. In this case, your squared variable is gone. You're solving for y. It's to the first power. You have a single solution. All right, number 3, graphing inequalities. We've done linear inequalities before. Now we simply need to graph quadratic inequalities. So what are the possibilities? You know, it could be less than, it could be less than or equal to, it could be greater than or equal to, right? It's going to be one of those. And if you got to graph it, we want to put it in graphing form, right? And so let me just real quickly refresh your memory. This is when you have both a horizontal and vertical shift. Remember, H shifts the vertex horizontally, left and right, and K shifts the vertex vertically, up and down. We could have a more simplistic form, right? And I think, let's see, let me look at our examples. All right, so none of those are, so you can have just y equals ax squared plus k. No horizontal shift, just the k, a vertical shift. So the vertex is going to be 0, whatever k is. And again, less than or equal to, less than, greater than or equal to. Or you could have the even more simplistic y equals ax squared. And again, it's an inequality, so less than or equal to, greater than or equal to. No shift here, right? No horizontal shift, no vertical shift. Vertex is at the origin. So vertex 0, 0, and away you go. All right, so all the 3 forms, this is full-fledged. A little bit more simplistic, no horizontal shift. Even more simplistic, no horizontal, no vertical shift. For some reason, students tend to mess up on the easier ones after a while because they forget because we're into the more complex. All right, so we know all this stuff. Less than or greater than, use a dotted line. You remember. less than or equal to, greater than or equal to, use a solid line. So dotted or solid. If there's no line underneath the symbol, it's dotted. If there's a line under the symbol, it's solid. And then in your shading aspect, if it's greater than or equal to, you have to shade above the parabola, because greater than values are above. And therefore, then, if it's less than or equal to, shade below the parabola. Below. Okay, so just a couple quick examples here. In this first one, if it were a less than or equal to, we used a solid line because of the equal to part. And less than would be, would you agree, below? Right? So I'm below, but look, I'm also then all around here, right? I'm really outside the parabola on this one. And the parabola is the barrier. So just start below and then just continue on that side of the curve. In the second example, you're just less than. So that's why our line was dotted. And again, where do you see less than? In this case, you're inside because it's a max. This one, third example, greater than or equal to. We used a solid line because of the equal to part. Greater than, you got to go above, which tells you, hey, where am I? I'm outside the parabola. So just keep shading everything outside the parabola. And just to cover the last possibility, if you go back to the first one on the left, if that would have been a greater than or equal to, then your shading would have been inside, right? Where the greater than values are. Pretty simplistic. If you don't like the above-below approach, you can always choose a test point. Pick the coordinates of any point, either inside the parabola or outside. Put it back into the function for the parabola and see if it's true or not. If the test point is true, all values on that side of the parabola are true. If the test point is false, on that side are all the false values, on the other side are all the true values. But again, it's pretty simplistic, above and below. But again, if you need to, use test point. All right, let's do a couple graphs. So you look at E. So it's an inequality. And I'm getting ready to graph this. And what's the first thing I want to do to get ready to graph this? Say it. Okay, vertex. So where are the coordinates of the vertex? Hopefully you say 1, -4, right? Not -1, -4. 1, -4. Remember, read the H value after the negative sign. Is this a max or a min? Say min. And our line of symmetry, therefore, is x equal 1, right? X equals the x coordinate. So that's always the first point you're graphing. So I'm at 1, -4. So it's right there. Line of symmetry. This is a min, so I know I'm heading up. Is this thing relatively wide, flatter, or relatively narrow, steeper? Wide, because of 2/3. What if it were -2/3? Would it then all of a sudden be relatively steeper? It'd still be wide, right, because it's the absolute value. So absolute value, anything less than 1, we're going to call wide or flatter. 1 or greater, I call narrow or steeper. The book calls 1 the same. All right, whatever. XY chart, right? XY chart. So again, take note, where are we at? We're already at an X value of 1. If you guys want to do fractions, you want to avoid fractions. So you're looking at this 3 in the denominator. So I want to go 3 away from where I am right now. I'm at 1. I'm going to go to 4. 3 away from where I am right now. So just to be clear, look what happens. So I'm taking the original, and where the x is, I'm putting in 4, right? So 4 minus 1 is 3. 3 squared is 9. But 9 divided by 3 is 3. 3 times 2 is 6. 6 minus 4 is 2. And 4 is 2. So right there. And that is 3 away to the right of the line of symmetry, and I'm going 3 away to the left of the line of symmetry. So again, if I wanted to avoid fractions, the next point I would use would be 3 away from 4 is 7, all right? Because again, it's got that minus 1 inside, and that's really going to end up using a 6, right? But again, if you'll just go from your vertex, 3, and then 3 again, the math will take care of it. So this time when you do a 7, 7 minus 1 is 6. 6 squared is 36. 36 divided by 3 is 12. 12 times 2 is 24. 24 minus 4 is 20. And you can see we're off the charts. So 4, 5, 6, 7. So 7 is way up there. Who knows? Somewhere off into the sky. So it's going up there. All right. Solid line or dotted line? Solid or dotted? Dotted. So let's just dot off to the left. Let's dot off to the right. Are we done? Finish it by doing what? Where do I shade? Above. So where's above? Right? In this case, we're inside. And away we go. So really doing these, we're kind of getting some practice with graphing as well. Any questions on that one? Okay, so let's do the last example. Okay, so you look at this thing, and hopefully right off the bat you notice that the y is not isolated. Do you agree? So we definitely got to move that y. And so hopefully you say, hey, let's divide the other side by -2. But I'm also remembering one other thing that's important, right? What do I have to do? Say it if you know it. You got to switch or flip the inequality symbol, right, whenever multiplying or dividing by a negative quantity. Okay, so where are we at now? We're at -x squared plus 4x plus 1. So what am I going to do now? If you were graphing this, what would you do next? Anybody raise your hand, tell me what to do next? You're graphing this, what are you going to do next? What are you going to do? Any volunteers? Come on, think. Julia? Well, I don't know if I want to use the quadratic formula. I could get zeros using the quadratic formula, but I really want more than zeros. What would you do? Luke? How are we going to do that? So, exactly, we want to put it in the graphing form, and to do that, we've got to complete the square. So, how do you complete the square? Isolate your variable terms, right? I want to factor out the negative. Do you agree? We want that lead term to be positive. So I'm at y less than or equal to negative the quantity x squared minus 4x. I still have the plus 1 outside. Completing this square. All right, somebody tell me what to put inside. What value goes right here? Josh? +4. So Josh took the b value, the 4. He divided it by 2, and then he squared it. So 4 divided by 2 is 2. 2 squared is 4, and Josh correctly put a positive 4 inside. So I got a positive 4 inside. What goes outside? Huh? I have a positive 4 inside, right here. Did I say negative? I don't see what are you guys saying? Okay. Hold on. You might be in the same place, just different terminology. Right there, we have a negative 4 inside. Inside the parentheses. Okay. With a negative 4 inside, what do I put outside to keep this balanced? Do I keep saying negative 4? Is that what I'm doing? The brain sometimes, you're thinking one thing. So with a positive 4 inside, technically, it's a negative 4, right? And therefore, we add its opposite, which is a positive 4 outside. Yes. If I said you had a negative 4 inside without any explanation, half the people in the class are thinking, no, it's a positive 4. But when I said there's a positive 4 inside, half of you are thinking, no, it's a negative 4. Well, yeah, technically it's a negative 4, right? Because of the negative out front. All right, we all clear as mud now? Let's finish completing the square. Y less than or equal to minus the quantity. Go ahead and finish completing the square. Why don't you finish graphing that from there? So finish completing the square and finish graphing it. I'm going to pause. So the first thing I determined was whether it was a max or min. So it's a max. It's at 2, 5. Line of symmetry. X equal 2. Plot the max point. Line of symmetry. XY chart. I did 3 and got 4. So I did the point 3, 4. Did the other point. The other's the line of symmetry. I did the point 4 and got 1. So point on the right. Same point on the left. Now, some of you would quit right here, but I don't have the whole bottom part of the Cartesian plane, and I'm going to do one more point. And if I do 5, I get negative 4. So I get a point there, which is 3 to the right of the line of symmetry, so I go 3 to the left of the line of symmetry. Now I have enough points. It is less than or equal to, so I'm going to do a solid line. And less than says shade below. And in this case, that's inside. Looks like cousin it. And inside you go. How many had that correct? Not good. Not boding well for you come Thursday. Better change it between now and then. But you all practice tonight. So homework tonight. Remember, test on Thursday, last test of the semester for you. Last opportunity to affect your grade.